So let us start with our last talk for this session. It will be given by Georgii Riabov on strong stochastic flows on metric graphs. Please, Georgii.
Okay, thank you. So I have a low connection, so probably I will turn off video. Okay, so the object of my research is strong stochastic flows on metric graphs. I will start with the definition of a stochastic flow. So I will work in a locally compact separable metric space. Then a stochastic flow on space M is a family of random mappings with the following 6 properties. So if we consider these mappings as a random process on M indexed by X of M, then it must be a measurable process. It satisfies evolutionary property in the sense that composition of 2 mappings psi rs and psi st is equal to psi rt. It has independent and stationary increments with the properties 3 and 4. And properties 5 and 6 are some continuity assumptions which will not be so relevant for me in this talk. And please note that the second property, which is evolutionary property, it holds almost surely. So for each family R, S, T, and X, the property holds almost surely. It means that exceptional set depends, in general, it can depend on moments of time and also on X. So when we fix a trajectory of this stochastic flow, it may happen that somewhere the evolutionary property breaks on this trajectory. So a convenient way to describe stochastic flow in general setting is to consider its finite point motions. So when we fix n starting points and B is a Borel set in m to the power n, then the probability that the flow will send these points into set B, it is a transition function on m to the power n. So it follows from independence and stationarity, like of increments of this flow. And this transition function, it is a sequence of transition functions. It is consistent in the sense of condition 2 below. Okay, if we take n trajectories and then the distribution of n trajectories defines the distribution of smaller number of trajectories. So it's like a consistency, and it has so-called a coalescing property. So if we consider 2 trajectories that start from one point, then it must these 2 trajectories must coincide. Also, I will assume that transition functions generate Feller's semigroups on corresponding spaces. So under these properties 1 to 3, it was proved that one can recover the stochastic flow. So if a sequence of transition probabilities satisfies properties 1, 2, 3, then there exists a stochastic flow on M with such endpoint motions. So this is a theorem of Lejeune and Raymond. For me, the most important part will be that flows constructed in this theorem, they are weak flows. A weak flow, by a weak flow, I understand a flow for which this second evolutionary property holds almost surely for fixed times and space variable. Okay. in the theorem of Lejeune and Raymond, the important step of the proof is to construct first one random mapping with the right distribution. So first they construct a mapping phi t of x, and it is done using so-called measurable selection. We can construct the random mapping phi t of xn. We can construct it using Kolmogorov theorem, so it will be like a countable family of random variables, and then we can define phi t x for each x as a limit point of a proper approximating subsequence. And what is done after that, then we take many independent copies of this mapping and try to couple them to get a stochastic flow. This approach can only gives weak evolutionary property. It holds like for dyadic rational numbers, but then one has to pass to the limit in some sense, and then the strong evolutionary property fails. Okay, this is actually the object of my investigation. I will say that a stochastic flow is a strong flow if the exceptional set where evolutionary property fails is independent from R, S, T, and X. And in many situations, it is known that a strong flow exists. So in the smooth case, when we have a flow of solutions to SDE, it was proved by Kunita. For Howitt-Warren flows, it is also known. It is known for stochastic flows of solutions to singular SDEs and also on some metric graphs. And I studied the situation with coalescing stochastic flows on the real line. Okay, this is the main problem of my research. I additionally assume one more condition on one-point motions. This condition ensures continuity of trajectories. Okay, so if I have a sequence of transition probabilities that satisfy, it must be 1, 2, 3, and 4 conditions, does there exist a strong stochastic flow with proper endpoint motions? A related, slightly stronger question is, we know that a weak flow exists, so does this flow possesses a modification which is a strong flow? And the idea of approach is directly work with the trajectories. So first, to get some sequence of sufficiently many trajectories of the flow and try to recover the flow, taking some using approximation and taking limit points. Okay, to move in this direction, I introduce the space of trajectories. Okay, so X, it is a space of all continuous functions in M that start at all possible moments of time. So actually X is a space where trajectories of the flow live. For each trajectory, I define the starting time by I of F, and we can extend it as a constant function to the whole real line and equip X with the following metric. So this metric, it captures the difference in starting times, and second summoned, it means just the uniform convergence on compact sets. Okay, the space X with this metric, it is a complete separable metric space. Since I will construct some sequences of trajectories and choose limit points, I need a result that allows me to choose limit points in the measurable way. So first, let's consider the notion of the skeleton. Phi n is a sequence in X. So it is a sequence of continuous functions in M. By I of S, I denote trajectories that started before time S, and ISK, I denote trajectories that started before time S, and at time S, they were in the set K. Okay. So this sequence will be called a skeleton of the flow if it satisfies evolutionary property. I mean, when two trajectories meet, they must move together. At any time S, values of this skeleton form a dense set in M. And if I consider trajectories that were in the compact set K at time S, then I will get a relatively compact set of trajectories. So why I need a property number 3, it will be clear in a moment. Okay, and I will say that a family psi is a flow extension of the skeleton if this family is a family of continuous functions, and properties 2 and 3 are evolutionary property, and property number 4 means that this family psi extends a sequence phi. By the way, it is an interesting and not clear question. If we have a skeleton, can we always construct a flow extension of it? This is not a probabilistic question at all. It is known that if we remove the first condition, we can construct such a flow extension. Okay, now I will try to construct such extensions using measurable selection. So recall that X is a complete separable metric space. It is a general result that for any complete separable metric space, one can find a measurable function that takes a sequence in X into an element of X with the following property. If the input sequence is relatively compact, then the result is a limit point of this sequence. So in any complete separable metric space, one can choose, one can construct a measurable selection function. So it is a function that chooses limit points of relatively compact sequences in a measurable way. So we can fix such function for our space of paths, and then we proceed as follows. So take any sequence of functions epsilon k that converges pointwise to 0. Now for each s and x, I pick the first trajectory from the skeleton that was at time s close to x. And how close it is given by epsilon k of x. So this gives me approximating sequence phi k by assumptions on the skeleton. This sequence is relatively compact. Okay, because it at time s it belongs to the ball, and we have a locally compact space. Then I apply the measurable selection mapping to this sequence, and I get theta s x. Unfortunately, this mapping theta, it may not be a flow extension. Theta may not satisfy evolutionary property, and it happens when trajectories from the family theta, when they pass through so-called exceptional points. Now I will give the proper definition. Okay, let's consider 2 moments of time, s and t, and fix x. And by kst epsilon x, I denote the closure of all trajectories that that were epsilon close to x at time s. And again, from our assumption on the skeleton K, the intersection in epsilon is an empty compact subset of continuous functions. Actually, it is a set of all possible limit points. So by nu, I will denote the number of points in K. And by tau, I will denote the first time when nu is at least 2. Now we can define the set of exceptional points. These are points such that when we start from point Sx, we immediately have several possible limit points approximating from the skeleton. So we have somehow to deal with these exceptional points. So again, I repeat that evolutionary property can fail at these exceptional points. Okay, if we didn't reach the moment tau, then we have one possible limit point I denoted by fsx. And it is an easy observation that if tau is finite, that exactly at time tau, this unique trajectory, it hits the exceptional set. And one more notion that I will need. The set of exceptional points, actually, it depends on the skeleton. And I will consider random skeletons. So when it can be an issue that to discuss measurability properties of this set E. To deal with this, I introduce the notion of measurable shell. So it is a family of closed subsets, which is measurable in the sense given in item 2. Yes, so the distance to F is measurable in S, X, and phi. And F contains E for all phi. Okay. Now, by sigma, I denote the first time function F hits this measurable shell. By definition, sigma is not greater than tau, and when we start from F, sigma is equal to S. So at time sigma, function F must be in the set F capital. Okay. Finally, I can define a candidate for a full extension, and it is defined as follows. I start from X at time S, and until my trajectory didn't hit set F, it is equal to theta. Yes, it is the unique limit. It is the unique limit point that exists at point Sx. And when we hit the set F, we change the trajectory. Okay, so it works as follows. We have a starting X at time S. So until we have a unique limit point, we follow this limit trajectory, and when it hits exceptional set, we change. So we make another choice of limit point now from this moment of heating. It occurs that with this definition, we already have the evolutionary property at time sigma. And next, we can show that this family psi, it is indeed an extension of the skeleton. So it preserves the trajectories of the skeleton. So I will not maybe say the proof. And the important result is that when we take a skeleton phi, then psi defined above, it is a measurable in all arguments transformation of the skeleton. Okay. I will skip the proof and show the main result. Okay, so we have a skeleton phi. We define psi. Still, psi may not be a strong flow, and I give a sufficient condition for this. The condition reads as follows. So after we hit exceptional set, our trajectory must coincide with some trajectory from the skeleton. So then we check that psi is a flow extension of the skeleton phi. Okay. The proof is quite long because we have to consider different cases when our points are exceptional or not. Okay, I will not maybe give the details, and I will show how to apply this theorem. So now assume that we have a compatible sequence of coalescing Feller transition probabilities. We know that a weak flow exists. The idea is first let's sample a skeleton from this weak flow. And then we redefine the flow in some different points. So by epsilon, I will denote the smallest radius such that the distance between trajectories from the to x, it is small enough. Okay, using this epsilon k, we can define approximating sequences and a family psi. So it turns out that psi is actually a modification of psi 0. And we achieve it using the definition of epsilon k and the Borel-Cantelli lemma. So with probability 1, approximating sequence has only one limit, which is psi 0, and it follows that psi is a modification of psi 0. It follows that once the condition from theorem 1 is satisfied, we get a strong flow. And there is one sufficient condition when this happens is when the skeleton has instantaneous coalescence property. It means that the skeleton maps space M into a locally finite set for all moments S and T. Then conditions of theorem 1 can be verified and we get a strong flow modification. Such instantaneous coalescence is typical to stochastic flows, so-called coalescing stochastic flows like Aratia flow. So they are studied. So these are the flows on the real line. And I will show on the metric graph a generalization of such flows. So
excuse me, just to tell you, you have 5 more minutes.
Okay, thank you. So then in the last minutes, I will show applications to metric graphs. Okay, this is a definition. I think it is more or less well known. I consider metric graphs where each vertex has a finite number of neighbors. Okay. And I want to show a sufficient condition that implies instantaneous coalescence property on a metric graph. So we have these two, we consider 2-point motions. Rho is a distance on the metric graph, and assume that for some positive p, we have the following estimate. So the probability that two trajectories from the flow, they will meet during time c rho square is at least p. So it is bounded from below. They must meet during the time which is proportional to the square of the distance between starting points. From this, one can prove that the skeleton maps the whole metric graph into a locally finite set. This condition was proposed by Evans, Morris, and Sen. They considered compact metric spaces. It turns out that for metric graphs, it works even if they're not compact. So for locally compact also. Okay. I will skip the sketch of the proof because it basically repeats the arguments of Morris and Sen. And actually, this condition is typically satisfied by processes that have some kind of self-similarity. So when we take independent Brownian motions, then they start from x and y, and the probability that they will meet before time c times distance squared is, it can be computed explicitly. Actually, it is independent on x and y. The same we have for independent Brownian motions, for reflected independent Brownian motions. Actually, one can consider arbitrary star graph and arbitrary independent Walsh-Brownian motions on this star graph. Again, the probability of meeting. In this example, also the Evans inequality is satisfied, so we can get analogs of the Aratia flow on metric graphs. Instead of independent Brownian motions, we can get independent Walsh-Brownian motions. This can be even further extended because one can consider arbitrary metric graph and like a Walsh-Brownian motion which has a different probabilities of choice at every vertex. So one can also construct such stochastic flows. And the last example I will show, it is an example of the flow that demonstrates mixed behavior. This is a flow of solutions to Tanaka SD. Such flow was studied by Lejean-Raymond, but it turns out that our framework allows to construct corresponding flow directly from the skeleton. In Tanaka SD, trajectories of the flow, they move parallel until they hit zero. And at zero, they coalesce. So this flow demonstrates mixed behavior, and it is possible to verify our theorem 1, yes, assumptions from theorem 1 for this flow as well. Okay, and the last I will say that the example with the smooth flows, it also fits our framework, because in the smooth flow, you don't have exceptional points at all. Okay, this is all what I wanted to say, so thank you for attention.
Thank you. Okay, some short questions before the lunch, maybe.
May I ask my usual question? What about other boundary conditions? So if we have not Walsh process, but more other different boundary conditions in a star graph, we have one vertex, but
now it is a research in progress. We want to consider Tanaka SD on a star graph. When each edge has an orientation, yes, and the trajectory moves along Brownian motion or minus Brownian motion depending on orientation. So the strong belief is that everything will work here. Also, one can consider interfaces D, where you have independent Brownian motions on different edges.
Yes.
It is still in progress, but we still hope that it will be done.
I also hope that's yeah. That at least Brownian motion on a graph, on a star graph with some boundary conditions in the vertex can be done.
Yes.
Okay, thank you.
Okay, are there any more questions? I was a little bit confused at the end. So you only consider star graphs? No?
I talked about them as an example.
In the examples, there were star graphs, or
yes.
If you show the previous example, for example, here, yeah, this Arasha flow.
Yes.
So this was for the star graph, or
this is actually this is for real line. For star graph, we replace Brownian motion by Walsh-Brownian motion, and the similar estimate is proved.
And then you take some.
I didn't put it here.
And then you take some distance, like instead of x minus y, you should take some distance, or
it's a geodesic distance on the
geodesic distance. Okay. But but then this would also work for general graph or just star?
Yes.
Yeah.
It actually, I will show that this estimate that I write here, it is too strong. If we prove the same for trajectories that stay in a compact, we still can apply our theorem. It means that actually we need only localized version of this estimate, and then everything reduces to star graphs, because a metric graph is locally a star graph.
Okay, thank you. So any more questions, comments? No, then just let us thank Georgii and all the speakers of this session.